Welcome to 63rd lecture. Remember that in my last lecture we reached up to this point. My goal was to find out what will be the voltage available across the armature terminals when no load is connected, open circuit condition, you have passed a DC current in the field winding, it has produced a flux per pole phi. Then my question was what will be the voltage induced in that. I know brass between the brass there will be several circuits in parallel, that is all the armature conductors will be divided into several parallel paths. My plan is okay, I will calculate the voltage induced in a single conductor and then I will multiply this expression with the number of conductors presented in a parallel path. One should not tell that this is the induced voltage in a single conductor, average induced voltage, and suppose Z is the total number of armature conductors, just do not multiply it with Z by A, Z, then it will be wrong, because all the parallel paths have definite number of armature conductors. So, I will start from here, that here I will say that the last day's expression induced voltage, we have got induced voltage in a single conductor, in a single conductor we got it to be is equal to B average, V velocity, V L V length of the conductor, V average, and this I found out to be V average is flux per pole is phi divided by the area over which this flux per pole will enter into the rotor, and that is equal to pi d by p into L. This is the area, I got B average, L is L and velocity is pi d n, where n is in RPS, armature rotations. This is the thing, and so this will be equal to phi p by pi d, L cancels out, into pi d n. Oh, this also cancels out. So, it is equal to phi p n, so much volts. That will be the expression for voltage in a single conductor. Now, I will say let Z be the total number of armature conductors. Total number of armature conductors. What do I mean by that? Armature has a coil like this. Armature has a coil like this, which may be multi-turn, coil. In each slot, how many coil sides will be there? 2 coil sides. So, in a conductor, in a slot like this, here I draw in a slot, there is the upper deck, multi-turn coil, section of that, and another coil side, multi-turn coil. Got the point? Therefore, if it is suppose having 2 turn, then 2 sections you will see, 2 conductors. For this also 2 conductors. So, multiply each coil with that multi-turn number. If it is a 2-turn coil, multiply with 2, then with another 2 for this one. So, total conductors means these conductors also which, because they will become seat of EMF, is not, they are having same velocity, same flux density they will see. All the coil sides in a particular slot will have same voltage V average L V. Suppose Z is the total number of armature conductors, and I hope you know how to calculate it. If S is the total number of slots, how many coils are there? S number of coils are there. If S is the total number of coils, how many coil sides are there? 2 into S coil sides are there. And if I say each coil has 4 turns, then 2S into that 4 is that number Z, total armature conductors. Okay. Let this, and also this thing I have defined, A be the armature parallel paths, number of parallel paths in the armature, that is a good English, number of parallel paths in the armature circuit, that is between the brushes. Across armature terminals, that is good, across the armature terminals, across the armature terminals. Because we have seen, at least in case of lap winding, it between the brushes it is divided into as many number of parallel paths between plus and minus brushes as the number of poles. And this, so I take a general case, okay, let the number of, because I have not yet investigated wave winding, maybe the number of parallel paths will be different. So, that is why a general variable name is given of the parallel paths. I am certain about one thing, that this is equal to P if lap winding, this much I am sure about lap winding. So, better use a general variable name parallel paths. Then how many conductors will be there in each parallel path? So number of conductors in each parallel path will be equal to Z by A, what else? Equally divided. Therefore, voltage available across the brass, available across the brass or armature terminals will be simply voltage in a single conductor multiplied by Z by A is phi p n into Z by A, that is equal to P number of poles, Z total number of conductors by A number of parallel paths into phi into n, that is all. Such a simple expression. So, what I mean to say is, now this, if you have a DC machine like this, if you pass some field current and it produce a flux per pole phi, and you allow this to run with a speed, let me change the color, it is not good, n, then voltage across this voltage across a A1 A2 E A1 A2 will be P Z by A into phi into n. In this formula, mind you, n is in RPS, phi is flux per pole, P and A are numbers, Z is the conductor. Okay. So, this is the most famous formula for a DC machine. If a DC machine, you know the flux per pole, if you know at what RPM or RPS it is running, if you know the total number of conductors, total number of poles of the machine, you can easily calculate what will be the generated voltage. Very simple formula. In case of AC machines, we used to have RMS voltage as 4.44 A, phi m, N1, winding factors, this, that, but here everything goes very simple, neat. And sometimes if the field circuit is assumed to be linear, then this phi can be related to IF by a linear relationship, and we say okay, here the induced voltage will be, if phi is proportional to IF, which will be at least in the linear zone of BH curve, then generated voltage, this A1 A2 will be also can be, see, Pz by A is a constant of the machine. Once the machine has been manufactured, number of poles Z, A are fixed, you cannot do anything with that. So, it is sometimes written like this, machine constant K phi n, where K is this, and generated voltage can be also sometimes written with this K and this phi with some constant, say K dashed into IF into n, if it is linear magnetic circuit. So, that generated voltage is proportional to IF into n. It looks like for a fixed speed, go on increasing the field current, your generated voltage will increase, and such an arrangement for producing voltage, also I will tell you the name, is called a separately excited DC generator. That is, field winding requires a separate excitation from DC source here. You require a DC source to pass this DC current through the field winding to create flux, and then of course, there should be a prime mover to drive the armature and you get a voltage generated. Okay, this is the one of the most important formula. Okay. Another formula, important formula is there, that is called the expression for torque, electromagnetic torque. Okay. If there is no load connected, just try to see what I am trying to tell. This is suppose the field winding. We will now refer to this simplified diagram, okay? And this is your armature terminals. Okay? You pass some field current, please try to follow me. Suppose this is the IF, and because of this IF, where you have connected perhaps a potential divider connection you do, and you can vary the field current also, okay, plus minus. You require a DC source, like that, and it is a separately excited DC machine, field winding is excited. Now, here what I am telling, of course, there will be a generated voltage. Suppose the flux per pole produced is phi. Phi is the flux per pole. And suppose you are driving the machine at 10 RPS, suppose in this direction. Okay. Then from this diagram, I am not sure whether I will not be able to tell whether this is plus, this is minus brass, that is not possible. But what is possible is, there are conductors here. I am drawing a representative conductor, and this pole is what? Not pole. If I show the poles also to complicate the matter, this is suppose the over which this field winding is wound. It is not correct to draw like this, but this side flux is entering to the conductor, better I will not show like that, it will only create confusion. So, I have in my back of my mind, it is like this is the field winding. If IF is like this, then this is phi f, that is what I mean. So, other side there is a south pole, is not? Lines of force will go in. So, it is south pole, here it is emanating. So, this is the flux per pole. In this simplified diagram, it is drawn like that, and you can always think that okay, there is a south pole which will absorb these lines of force here after cutting the armature conductors. Now, what I am telling in this diagram, so this is right hand rule I will apply. What will be the polarity of this induced voltage? It will be right hand rule B, that is from left to right. Okay. This is the B, and direction of rotation is like this. So, this is the right hand rule I am applying. B velocity for this conductor is in this direction, V, it will be cross, is not? It will be cross. And you can be rest assured, if you apply the same rule, velocity is same, but it is under south pole, it will be dot. This is what, and for all the conductors, whoever is here, that will be cross only, is not? And this will be dot. Now, out of these two, which brass is plus or minus, difficult to say from this. We will assume this is plus minus, for that nothing is going to change, because it is the armature current distribution which matters. You assume this is plus, this is minus. Okay? And suppose you make an arrangement, DC voltage you will get. So, loads will be, if it is generator mode, that is what I have assumed, I will connect a resistive load, switch is opened. With switch open, this voltage here is the open circuit voltage, is given by P z by A phi into N, so much volts you will get. What will be the armature current? Armature current is 0. This cross and dot here shows the polarity of the induced voltage, mind you, these are all dot on this side under the south pole, and these are all cross. But it will drive a current, if the switch is closed, it will deliver a current, external current I A. Will this current be same as this current? No, I know between the brushes there are parallel paths. So, current in the conductors will be this current divided by A, and what will be their directions? These directions I am certain it is absolutely correct. With this direction of motion, this being north pole, this is the thing. So, this is the current and they get divided in cross and dot. It looks like a two parallel paths in this simplified diagram, but it is not, we know that. Anyway, now the question is, the moment so long with S opened, these conductors were not carrying any current. Prime mover was running this generator at some speed in the clockwise direction. How much torque the prime mover had to apply so as to make it run in the clockwise direction? Opposing torque was maybe some little friction torque, a little, that is fuel consumed by the prime mover at that time was very little, less, just to overcome friction to run it at a constant speed. Now, you close this switch. The moment you close this switch, you see there appears current in this direction, all the conductors here cross dot. If that be the case, then they will experience force, and once again I will apply right hand rule to find out the direction of the force. So, mind you, the prime mover is giving a torque in this direction, T p m torque by the prime mover. Now, the moment you give this, try to extract power from the armature of the DC machine, this is R L load resistance, current will appear, and then the conductors will be carrying also current in the same direction as the induced voltage, and apply left hand rule to see that it will experience, these sides will experience a force in this direction, in the opposite direction of the prime mover torque. Prime mover thing is a mechanical thing, who is providing you the torque, electromagnetic torque. And if you find the generator is supplying power running at a constant RPM or RPS, you will conclude the prime mover torque and electromagnetic torque are same. That is why it is running at a constant speed, because if prime mover torque wins over electromagnetic torque, it will accelerate in this case. If electromagnetic torque is greater than prime mover torque, it will decelerate. So, it is a generator mode, it goes like that. We will come to this aspect many times later, but for the time being what I am telling that okay, the moment armature carries currents, conductors will experience force, hence torque. How to get an expression of the electromagnetic torque? That is what we will be discussing. So, to find that out, what we will do is this: we consider suppose a 4-pole machine, just for the sake of suppose you imagine very interesting calculation from the fundamental we will do. Suppose 4-pole north south, north south, field windings I am not showing. Here are armature and these are the conductors on the slots, periphery of the armature, like this. Suppose a 4-pole machine. Now, you divide this in 4 zones, that is this is the zone of magnetic neutral axis, these are called, where the flux density will be 0, etc. So, this zone is controlled by the south pole, this zone is controlled by 1/4 controlled by this north pole, this 1/4 zone, quarter zone is controlled by south pole, and these are the 45-degree lines you draw. And as I told you that if you assume, because this diagram will not tell you the true pictures. Why? Because it is a very simplified schematic diagram of the whole things. But if I want to calculate the expression of the torque, I have to refer to this and say that okay, machine is running in the anticlockwise direction with a velocity n rps. Same. Then I know the currents in the conductors under the influence of the north pole will have cross. So, I put cross here. Suppose the number of poles of the machine is 4. So, these are all cross. Are you getting? Cross current. Whichever conductors are under south pole, they will have dot. What else? Similarly, these conductors cross. And these conductors once again dot. We have got. Then how the torque will be produced? I take any conductor here, suppose this conductor. Put attention to this. What is the force it experiences? B, I and L. So, force experienced by a single conductor will be equal to B at this point into current through this conductor, not this total current, that is very important, and the current through this conductor is I A by A, that I know, that is very important, B I A into length of the conductor, just like the EMF equation I am going. And once again this conductor as it moves, we will see different values of B, but nonetheless direction of the force will be like this in the anticlockwise direction. Therefore, it is prudent not to deal with that B, but to take what is the average B it experiences, B average I A by A into L. This is, mind you, is A, slightly disturbed I A. This will be the force. So, average force experienced by a single conductor is this. What is the torque? Torque about the origin or about the shaft? Torque experienced by this conductor will be equal to the force into d by 2, that is B average I A by A into L into d by 2 radius, force into distance about this point. The interesting point is that it is true for all the conductors. If it is here under south pole, it will see once again same B average. And what will be the direction of the force of this conductor dot south pole left hand rule. So, this is forefinger is the direction of the current. it will also experience a force like this. What will be the torque contributed by this conductor? This into d by 2. What about this one? Same B average, same I A by L, d by 2, d by 2. Every one contributes. There is no conductor experiences a force which is the directions of which will change. Therefore, all the torques will add up, is not? Therefore, total torque experienced by a single conductor is this. Therefore, total torque electromagnetic torque will be B A I A by A into L into d by 2 into how many conductors should I multiply? Should it be Z by A? Should it be Z? What? It must be Z, because each conductor is contributing to the torque. Unlike the EMF calculations where there were several parallel paths Z by A, Z by A, and to calculate EMF you have to consider between the brushes, you have to consider only one parallel path, good enough. So, Z by A conductors, but in this case all the conductors, each of them, one of them is carrying a current of I A by A, and they are contributing torque in the same direction. Therefore, it must be multiplied with Z, not with Z by A. Therefore, finally, I will say that electromagnetic torque will be equal to B average, this is B average sir, B average I A by A is the current flowing through each conductor into L into d by 2 into Z, which will be equal to, I know B average is phi by pi d by P into L area, and this is I A by A into d by 2 into Z. Therefore, the expression of the torque will be torque expression will be L over L, I missed L, is not, that is what I mean. So, there is an L also on the top. So, this will become equal to, if you see several things cancelled out, is not, dl cancel out, dl cancel out, and it will be equal to, and it is 2. So, it will be equal to Pz number of poles Pz, P is there na, P will go up, Pz by A, not only A, 2 pi A into phi into I A. This is the expression of the torque. We will continue with this in the next lecture. Thank you.